Hi, everyone. So today we're going to do an introduction to related rates, and we're going to continue this work over the next couple days in class. So this is really the reason that we started doing implicit differentiation before we did this section, because related rates, what we're going to set up, has to do a lot with differentiation with respect to other variables. So our learning target says I can differentiate functions with respect to t. So we know that using Leibniz notation, notation like dy dx is asking us to differentiate a function y with respect to x. So when we're talking about differentiating functions with respect to time, that really just means that if our function is in the form of like an area equals something, then our derivative of that would be the derivative of area, or dA, with respect to time, dt. Or for example, if we had like a volume formula, so we would have something in the form of V equals, the derivative of that would be the derivative of volume, or dV, with respect to time, so dt. So the derivatives that we're going to be talking about today are going to look something like this. So they're always going to be differentiated with respect to t. So the idea of related rates is that we might need to find a rate at which some quantity is changing by relating that quantity to other quantities who we know the rate of change for. So we'll kind of just start off with a basic example, and then we'll look through a couple of application type problems of when we might encounter this. So for example one, we're given a equals x squared. We're given some information about dx dt and some information about, and we want to know about dA dt. So this dx dt is really telling us that this 3 is the rate of change of x, and we're taking the derivative with respect to time. So what we're going to want to do is we're going to want to take this a is equal to x squared, and we're going to differentiate that entire equation with respect to t. So the derivative of a is kind of what I talked about up here. We're going to write the derivative of that as dA dt. And then we're going to use some implicit differentiation here. So we know that this is going to have some power rule to it. So we know we're going to have some sort of 2x. But then we want to differentiate this x with respect to time, because this is going to be our chain rule here. We want to get the derivative of this x stuff too. And that's going to be written as dx dt. So this is the derivative of a with respect to time. We're saying it's equal to 2x times the derivative of x with respect to time. So then what we need to do is we just need to fill in what we have here. We know we're looking for dA dt, so that's going to be what we're looking for. So I'm going to bring that down. And that's going to be equal to 2 times x. Well, it's telling us that x is equal to 10 times the dx dt, which we know is the rate of change of x with respect to time. So that's going to be times 3. So our dA dt is just going to be taking all of those and multiplying them together. So 2 times 10 is 20 times 3 should give us 60. And dA dt here is going to be 60, which is the derivative of a with respect to t. So let's take a look at kind of a similar example. So just given an equation, we want to know a certain piece of information here. So suppose x is a differentiable function of t, and suppose that when x is equal to 15, the derivative of x with respect to time is 3. We want to know what dy dt is here. So this is what we're going to solve for. When x is equal to 15, and we're given this equation, y squared minus 625 minus x squared. And key thing here, which we'll use in one part of the problem, is that y has to be greater than or equal to 0. So this is going to be the equation that we want to differentiate with respect to time. So again, I'm just going to work my way left to right like we did with the implicit, and I'm going to take the derivative of each term, and I'm going to apply the chain rule when necessary. So I'm going to take the derivative here. This is going to be 2y. But I need to chain rule it, and I need to also get the derivative of y with respect to time. So I'll write that as dy dt is equal to, derivative of 625 is just 0, minus the derivative of x squared, which is going to look pretty similar to what we did in our last problem. So power rule tells us that's going to be 2x. And then we're going to multiply by the derivative of x with respect to time. So times dx dt. So then I'm going to start filling in what I have here. So I'm going to pull down the 2. But I'm noticing that right now I don't have any information about y. So we'll kind of come back to that in a second. I know that I'm looking for dy dt, so I'm going to leave that as my variable here. And then on this side of the equation, I'm left with a -2. We know that x is equal to 15. And we know that dx dt is equal to 3. So then I'm still missing that piece of information where I need to know about y. Well, if I have this equation, y squared is equal to 625 minus x squared, and I know what my x value is, I can actually use this function to find y. So if there's any piece of information that I'm missing, there should be something that is available to me to help me solve for that. So I'm looking for y squared equals to 625 minus x squared, so minus 15 squared. So y squared is going to be 625 minus 225. Y squared gives me, that's 400. And then I'm going to take the square root of that. And remember that the square root is technically going to be plus or minus the square root of 400. But this piece of information is telling us that the y value has to be positive. So when I take that square root, I'm just looking at the positive value, and that would be a 20. So that's what I'm going to go ahead and substitute in for my y over here. So that's going to simplify to 40 times dy dt is going to be equal to -90. And then to solve for dy dt, I'm just going to divide each side of this equation by 40. So dy dt would be -90 divided by 40. But I would want to simplify that as much as I can. So dy dt is going to be -9 over 4. So you'll notice that in the first example, we got a derivative with respect to time that was positive, and here we got a derivative with respect to time that was negative. So there is a significance of these numbers being positive and negative. And we'll kind of talk a little bit about that when we go through some kind of application problems. But just know that that definitely can happen. So let's start looking at some applications. So we're letting A be the area of a square whose sides have a length s, and we want to assume that s varies with time t. We want to know at a certain instant, the sides are 3 feet long and they're increasing at a rate of 2 feet per minute. How fast is the area increasing at that instant? So the last 2 examples, we were given an explicit function. We were given an equation for what we needed to take the derivative of. Most of the time, we are going to need to have to set up something that we can take the derivative of. And a lot of the times, there's going to be context clues. In this case, it's going to be the area of a square. And we want to know how fast the area is increasing. So anytime we're talking about an area increasing, a volume increasing, a surface area increasing, we know that we're going to have to do something with the derivative of whatever that formula is that we need to set up. So I need to let A be the area of the square. So I'm going to go ahead, I'm going to set up a formula for area. So my area is going to be A equals, and it's telling me that my sides have a length of s, so that's going to be s squared. And I'm going to want to differentiate, again, this function with respect to time. So when I do that, that's going to give me dA dt is going to be equal to, again, I have a power rule here that I need to work through, and then I'm going to take the derivative of s. So it's going to be 2s times the derivative of s with respect to time, so ds dt. And then I'm going to have to pick through this information to decide, well, what do I actually have here and what do I need? So at a certain instant, the sides are 3 feet long. So it's telling me through this piece of information, at that particular instant, s is equal to 3. That's how long my side lengths are going to be. But it's also telling me that the sides are increasing at a rate of 2 feet per minute. This is giving me information about the derivative. That's how fast the side length is changing. So this is ds dt and it's telling us that it's equal to 2. So that's the rate of change of the sides with respect to time, and that's 2 feet per minute. And here's really where the significance of the positive and the negative derivative come in. If it's telling us that we're increasing at a rate of whatever, our derivative is going to be positive. If it was telling us that we are decreasing at a rate, we would write that rate as a negative value. So just be careful of those keywords there. That's going to tell you what the sign of your derivative should be. And this is asking us, how fast is the area increasing? So if we want to know how fast the area is increasing, this is really asking us, well, what is dA dt? What is the rate of change of area with respect to time? So this is really what I'm solving for in this problem. What is the derivative of area with respect to time? I have the other 2 pieces of information that I need to fill in over here. So my dA dt is going to be 2 times 3 times 2, so 12. And in this case, because I do have units that are involved in the problem, I do need to make sure that I'm using units when I'm filling in my final answer. How fast is the area increasing at that instant? Well, my area is going to be increasing, and I know it's going to be increasing because my rate here is positive at a rate of 12 what? Well, if we think about the units on area, area is usually like feet squared or meters squared or miles squared. So that's where I'm going to start out. So I'm going to say, okay, 12, my units are here feet squared. But since we're talking about a rate of change, I'm going to also have to include the unit of time as well. So my dA dt is actually 12 feet squared per minute. So if I want to write it out in a sentence, the area is increasing at a rate of 12 feet squared per minute. So just a couple of kind of side notes here on notation, or actually on units, because I think that units are usually part of these problems that give some people trouble. So I just want to kind of give you guys a rundown on units. Anytime that we're talking about the rate of change of a side or of a radius or of some kind of length or distance, our units are generally going to be given as like, I don't know, feet per second, miles per hour, some unit of distance over some unit of time. So those are just some examples of what your units should look for when you're looking for a rate of change of sides or radius or length or whatever. And if you notice, that's what our units were here when we were talking about the sides increasing at a rate of 12 or 2 feet per minute. If we're talking about the rate of change of like areas, or sometimes you'll see that as like surface areas, your units are going to be something like feet squared per minute, or meters squared per second, or miles squared per hour. So your units are going to be squared if it's talking about area. If it's talking about a rate of change of volume, those units are generally going to be cubed. So examples of that would be feet cubed per minute, or meters cubed per second, or miles cubed per hour. So those are just kind of key things to keep in mind. Anytime you're talking about like a 2-dimensional rate of change, it's always feet per second, miles per hour, meters per minute, whatever it is. Rate of change of areas, you have squareds. Rate of change of volumes, you have cubes. So keep that in mind as we're kind of going through those other examples. Okay, so now we kind of get more into a little bit of geometry. So example 4 has to do with water leaking onto a floor with a circular pool. So keyword here, circular. The radius of the pool increases at a rate of 9 centimeters per minute. How fast is the area of the pool increasing when the radius is 3 centimeters. So here's the keywords to determine what I need to set up here. I'm really talking about an area of a circle. So I'm going to set up my area is equal to pi r squared. And this is going to be the formula that I want to differentiate with respect to time. So let's go ahead and do that. So dA dt is equal to, this pi is just a constant, so I'm going to use my power rule. So 2 pi r is my power rule, but then I need to take the derivative of r with respect to time, so dr dt. And then I'm going to pick through and I'm going to say, okay, what do I have? What do I need? So water leaking onto a floor forms a circular pool. The radius of the pool increases at a rate of 9 centimeters per minute. So this is actually my radius rate of change. So this is going to be dr dt. And since we are increasing, this is going to be a positive 9. And I want to know how fast the area of the pool is increasing. So what I need to know is what is the rate of change of the area. So I'm trying to figure out what is dA dt. At the moment when the radius is 3 centimeters. So this is telling me that my r is 3. So I'm looking for dA dt. And then I'm going to fill in what I have over here. So 2 times pi times the radius of 3 times the dr dt of 9. And generally we leave these in exact form. Like I wouldn't actually like make a decimal out of the pi. I'm going to write this as dA dt is equal to 54 pi. So again, since we're talking about the rate of change of area, our units are going to be something squared over whatever our unit of time is. So centimeters is our unit of length. So centimeters squared per minute. And if I want to write that out as a sentence, the area of the pool increases at a rate of 54 pi centimeters squared per minute. So the next example actually has to do with something a little bit different. So let's read through this one. Air is being pumped into a spherical balloon at a rate of 5 centimeters cubed per minute. So air is being pumped into a balloon at a rate of 5 centimeters cubed per minute. This right here, this power of 3, should indicate to me that I'm talking about a sphere's volume. Volume is always cubic. And I need to determine the rate at which the radius of the balloon is increasing when the diameter of the balloon is 20 centimeters. So the first thing I need to do is I'm going to say, okay, we're talking about a volume of a sphere. So if you don't remember from geometry, the volume of a sphere is volume is equal to 4/3 pi r cubed. And this is going to be the formula that I want to take the derivative of with respect to time. So if I take the derivative of v, that's going to be dv dt. This 4/3 pi is just a constant. So I'm going to apply my power rule here. So this is really going to be 4/3 times 3 times pi times the radius squared. And then I need to multiply, use my chain rule here to multiply by the derivative of the radius. So dr dt. I'm going to simplify that because my 3's actually end up canceling out here. So dv dt is going to be 4 pi r squared times dr dt. And then I'm going to go back and read through what I have. So I have the rate of change of volume. It's telling me that the air is being pumped at a rate of 5 centimeters cubed per minute. So this is actually telling me that dv dt is 5. And since air is being pumped into it, that means that the balloon's volume is increasing. So this is going to be a positive 5 here. I need to determine the rate at which the radius of the balloon is increasing. So I want to know how the radius of the balloon is changing. So what I'm looking for is dr dt here. And it's telling me that the diameter of the balloon is 20 centimeters. So my diameter is 20, but in my formula, I need to know the radius. So that would tell me that my radius would be 10. So I'm going to work up here. And I'm going to substitute in what I have. So dv dt we said was 5 is equal to 4 times pi. The radius here is 10, so 10 squared. And I'm looking for dr dt, so that's going to be what I'm looking for in terms of a variable, so I'll just leave it as the variable here. I'm going to simplify over here. So this is going to be 5 is equal to 4 times 10 squared is 4 times 100, so 400 pi times dr dt. And then I'm going to divide each side of the equation by 400 pi. So this is going to give me dr dt is equal to 5 over 400 pi. And anytime I can simplify a fraction, I definitely want to simplify that. So that gives me 1 over 80 pi. And this is talking about the rate of change of a radius. So the radius is just a unit of length. So when I'm talking about the rate of change of the unit of length, I'm just going to be using centimeters per minute. And again, if I want to write this out as a sentence, the rate at which the radius of the balloon is increasing is 1 over 80 pi centimeters per minute. And again, I'm not going to get a decimal approximation for that. I'm just going to leave it as its exact value here. All right, so example 6 is a little bit different. This actually is going to be a triangle problem. So a ladder 25 feet long is leaning against the wall of a house. So I'm going to make myself a little diagram here. Sometimes with these ones, it's easier to work from a diagram, so it might help to draw one. So here's my house, my wall, and my ladder is leaning against it. So I'm going to draw my ladder here. So here's my ladder. And I know that this ladder is 25 feet long. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. We want to know how fast is the top moving down the wall when the base of the ladder is 24 feet from the wall. So there's a lot of information that goes on to these types of problems. So the better that you label the diagram, I think the better off you're going to be in terms of figuring out what you need to do. So we actually have a right triangle that is being formed here because we can assume that the wall is going to meet the ground at a right angle. And what's happening is I'm taking this ladder and I'm literally pulling the end of it away from the house, which means that as I'm pulling it, the ladder is going to slip down the wall. So the base of the ladder is pulled away from the wall at a rate of 2 feet per second. So for these, I like to make arrows indicating which direction my kind of lengths are moving. So the base of the ladder is being pulled away from the wall. So that means that this bottom length is going this way. The bottom length is going to be increasing because as I move this ladder away, the bottom length aside or away from the house is going to be increasing. And that's at a rate of 2 feet per second. We want to know how fast the top is moving down the wall. So I want to know what this distance is changing. So I want to know how fast this is moving downwards, or the top of the ladder is moving down the wall as it's slipping away, when the base of the ladder is 24 feet from the wall. So I'm going to start assigning some variables here because I think with variables, it's a little bit easier to kind of label and see what we're talking about. A lot of times with Pythagorean theorem problems, we talk about like the lengths as being A and B and the hypotenuse being C. In calculus, generally, we talk about those lengths as X, Y, and Z. So I think about it kind of in terms of a coordinate plane. Usually I label the bottom side my X values because that's the axis that is horizontal. I label my kind of vertical values Y because, again, the Y-axis is vertical. And my hypotenuse I'm going to call Z. So this is giving me information saying that the base of the ladder is 24 feet from the wall. So that means at this instant, this X value or this X distance is actually going to be 24. So this 2 feet per second is actually the rate of change of X with respect to time. So that's actually our dx dt. What we're looking for here is dy dt. We want to know what the rate of change of y is with respect to time. So what I'm looking for in this problem is I want to know how fast this is moving down the wall. So I really want to know how fast y is changing. So let's set up an equation here. So obviously we're definitely going to want to use the Pythagorean theorem, x squared plus y squared is equal to z squared. So I'm going to go ahead and set that up. And this is going to be the formula that I want to differentiate. So I'm just going to work term by term here. So x squared, derivative would be 2x times the derivative of x with respect to time, so dx dt, plus y squared is 2y times the derivative of y with respect to time, so dy dt. And this is going to be 2z times the derivative of z with respect to time, so times dz dt. And I'm going to fill in what I know right now. So I know all of the information about x. So I know this is going to be 2 times the x value of 24 times the dx dt of 2. I know that dy dt is what I'm looking for here. So I know that I'm looking for dy dt. I don't have any information about y yet, so I'm going to leave that for a quick second. But I do have information about z. I know that that's 25. But I also don't know anything about the dz dt. So two things that we're missing here are y and dz dt. Well, if we have two lengths of a right triangle, we can definitely solve for y here. So I can do just the Pythagorean theorem to figure out what y is. So I'm going to set up my x squared, so 24 squared, plus my y squared is equal to my hypotenuse squared, so 25 squared. And then I'm just going to go ahead and quickly calculate that. So that's going to be 576 is equal to y squared, sorry, plus y squared is equal to 625. That's going to give me y squared equal to 49. And since we're talking about distance and lengths here, we're really only worried about the positive value. So my y value here is going to be 7. But then we still need to know about dz dt. Well, what does dz dt represent? Well, we know that this hypotenuse is representing the length of the ladder. dz dt would be representing the rate of change of the ladder. Well, if we know that we're not cutting our ladder into smaller pieces or we're not losing any part of our ladder isn't changing length. It's not ever going to change length. So the dz dt here, a little tricky, is actually just 0 because the rate of change of a ladder, the length of the ladder, well, ladders don't change lengths randomly. So we're going to call dz dt 0. And then what we can do from here is we can just kind of simplify what we have across the board here. So 2 times 24 times 2 is going to give me 96 plus 14 times dy dt. And this whole stuff on the right-hand side actually just ends up being 0, which actually makes that pretty nice for us. And then I'm just going to solve for dy dt here. So I'm going to move the 96 to the other side. And dy dt is going to be negative 96 over 14, which I will simplify to be negative 48 over 7. And in context of what we were talking about with negative and positive rates of change, this is telling us that the rate of change of y is actually negative, which makes sense because as the ladder slips down the wall, this distance of y is going to get shorter. If it's getting shorter or smaller, our derivative is going to also change in a negative direction. So our derivative here should be negative. When we do write out the answer to the question, though, we're just going to have to be a little bit careful about how we word this. So dy dt is definitely negative 48 over 7. But when I answer it in a sentence, how fast is the top moving down the wall? I'm going to say that the top moves down the wall at a rate of I'm just going to say at a rate of positive 48 over 7. So at a rate of 48 over 7. And this is just a length that's changing. So my unit of distance is going to be feet, and my unit of time is going to be second. So the top is going to move down the wall at a rate of 48 over 7 feet per second. So usually when we have a negative rate of change, we don't generally say that. Like I wouldn't say that the top moves down the wall at a rate of negative 48 over 7. The key word here is putting the down in, because that down is telling us that that length is getting shorter. So we got one more example with the triangle, and then we'll talk about a rectangle quickly. So example 7, this one would definitely be useful to draw a picture for. A boat is pulled in by means of a winch on a dock 12 feet above the deck of the boat. The winch pulls in the rope at a rate of 4 feet per second. We want to determine the speed of the boat when there's 13 feet of rope out. So I'm going to draw myself a little boat out here in my water. And my boat is approaching some dock over here, a little bit away. So there's my dock. I'm a math teacher, not an artist, by the way. So don't make fun of my drawings. So the boat is being pulled in by means of a winch on a dock 12 feet above the deck of the boat. So here's the deck of the boat. Maybe I should have made this a little shorter, but we'll work with it. So here's the deck of a boat. And it's telling us that this dock is 12 feet above the deck of the boat. So this distance from the deck of the boat up to the top of the dock is 12 feet. So from here to here. I know I just made that a little bit bigger too. Sorry. And there's this winch or this contraption here at the top of the deck that is attached to the boat, and it's pulling the boat in. So there's going to be kind of this diagonal piece here, and this is going to be a rope with the winch that's pulling it in from the dock. So what this ends up looking like is actually a right triangle problem. I know it kind of doesn't look like that very well because my triangle is a little bit small, but here's our triangle. So we know that our height of our triangle is 12 feet. It's telling us that the winch pulls in the rope at a rate of 4 feet per second. So what's happening is that this rope that's attached to the boat and the winch is actually being pulled in. So here's my direction arrow to show that this is coming in. And it's pulling it in at a rate of 4 feet per second. But we have to be careful here about our sign, because this length, as we're pulling it in, is getting shorter. I'm going to mark this as a rate that is a negative rate, because this distance is getting shorter. Our rate has to be negative. And then it tells us that the winch is pulling in the rope at a rate of 4 feet per second. Determine the speed of the boat when there is 13 feet of rope out. Well, here's our rope, again, connecting the boat with the dock. So this length here, which would represent, in this case, our hypotenuse, would be 13. So if it helps to kind of redraw your picture, you definitely can. So this is 12. I'm going to call 12 our y value here. This is 13, which is our z value. And since this is the rate of change of this z, I'm going to call this dz dt, and that's our -4. So I need to definitely probably figure something out about down here, but we're going to set up our formula here. So right triangle, x squared plus y squared is equal to z squared. Same derivative as the other problem that we just went over with the right triangle. So I know the derivative is going to be 2x times dx dt plus 2y times dy dt is equal to 2z times dz dt. So I definitely am going to need to know something about x. But again, since I know the other two lengths of the right triangle here, I can use the Pythagorean theorem to figure out what my x value is down here. So x squared plus 12 squared is going to be equal to 13 squared. So that's going to give me an x squared equal to 25. That's going to tell me that the x value down at the bottom here is 5. And I want to determine the speed of the boat. So if we're thinking about the boat is moving in this way towards the dock, what I really want to know here is what is this rate of change along the bottom here. So I want to know what dx dt is, because that's going to tell me what the speed of my boat is. So I need to figure out something about dy dt. What is the change of y with respect to time? Well, it tells us that the dock is 12 feet above the deck. The dock is not changing length. So this is going to be another case where we would say that the derivative, or our derivative of y with respect to time, is actually going to be 0 here. So let's go ahead and fill all this stuff in. So 2 times the x value of 5, we're looking for dx dt, plus 2 times the y value of 12 times dy dt is 0, equals 2 times z, so 13 times dz dt is going to be negative 4. And then I'm just going to simplify here. So this second term, it just ends up becoming 0. So on the other side, I get negative 104. Dx dt is going to be negative 104 over 10, which is going to give me negative 52 over 5, which again makes sense because as the boat is pulling in, this horizontal distance is decreasing. So that means that this rate of change should be negative because that distance is getting smaller. So dx dt here is going to be negative 52 over 5. But again, when I answer the question, I'm going to make sure that I answer it without this negative in it. So I'm going to say that the boat has a speed of 52 over 5. And this is just a length that's changing, so feet per second. And again, I'm not going to say that it has a speed of negative 52 over 5 because that's telling me that the boat is just being pulled in here. So this sign does not matter here. So we'll do one more that has to do with a rectangle. So a height of a rectangle is increasing. Okay, so at this time, I'm going to make myself a diagram here. So here's my rectangle. The height of a rectangle is increasing at a rate of 11 centimeters per hour, and the width of the rectangle is decreasing at a rate of 9 centimeters per hour. So here we actually have two different rates. One's increasing, one's decreasing. So I'm going to label one of my sides as my height. I'm going to label the other one as a width. And it's telling me that the height is increasing, so I know that dh dt is going to be 11. The width is decreasing, so dw dt is going to be 9, but because it's decreasing, it's going to be negative 9. And at a certain instant, the height of the rectangle is 3 centimeters, so height is 3, and the width is 8. And I want to know what is the rate of change of the area. So I need to know the rate of change of area. So I'm talking about the area formula of a rectangle. So area is just length times width, or in this case, width times height. And to get the derivative of this is going to be a product rule. So if I product rule this is going to be, I'm going to call my f my w. That means that f prime is going to be the derivative of w with respect to time, so dw dt. G is going to be the h. G prime is going to be the derivative of h with respect to time, so dh dt. So if I apply my product rule, my dA dt is going to be equal to my f prime times g. So I'm going to write that as h times dw dt, plus my f times g prime, so w times dh dt. And I have all of these pieces of information, so I don't need to find any of them. So I'm just looking for dA dt. That's going to be equal to the height of 3 times the dw dt of negative 9, plus my w of 8 times my dh dt of 11. So that's going to be negative 27 plus 88. And that's going to give me a rate of change of the area to be 61. And rate of change of area means that my units of measure are going to be squared per hour. So dA dt is 61 centimeters per hour. So when I answer this question, it's asking me what is the rate of change of area. I'm going to say that the area of the rectangle is actually going to be increasing. And I know that it's going to be increasing because this rate of change is positive. So I'm going to say the rate of the change, or rate of The area of the rectangle changes. I'm going to put in parentheses here, increases at a rate of 61 centimeters squared per hour. All right, so now it's going to be your turn to try some homework problems. Let me know if you have any questions.